that the full width half maximum due to the atmosphere is something like lambda over 20 centimeters. And there's a whole theory behind this, which is actually a reasonably good description of what the atmosphere does. And of course, this 20 centimeters depends on conditions. That's, you know, it's not that good in New York City, although it's not terrible. But it's very, very good in, you know, certain parts of Chile. So here we have. So here's what we've got. We've got our image, which is this noisy sample of a function. The function has some interesting properties, including the fact that it's the Fourier transform of a finite size distribution of rays. I don't have to erase anything. And so we should think about what one can do with such a sampling. And the first thing to talk about, which I'm sure you've heard of, is the Nyquist limit, or the Nyquist theorem, or the Nyquist sampling, or Nyquist something. And what this means is the following. Imagine I do have a sampling of a function for whatever reason. Now I'm calling it h of theta. Maybe I'll just call it h of x. This is a sampling of some underlying function. The spacing between these two, I'm going to call delta. And say you have this sampling as delta. There is a critical frequency which is fc over 1 over 2 delta, which you can write as a wave number, which will be 2 pi over 2 delta, or pi over delta. Such that if the Fourier transform of h is 0 for all k greater than this critical k, then this sampling determines h of x completely. So if the Fourier transform of this thing is 0 above, below some wavelength or above some k, then this thing is fully determined. And I could prove this mathematically, but you've probably seen it proven mathematically at some point. It's easier to see, what's the word, graphically. Also, I'm not that good at proving things mathematically. So let's look at the Fourier transform of the image. Here's minus kc, here's plus kc. I'm going to do everything here in 1 dimension. 2 dimensions is just a trivial. And if you imagine that this Fourier transform is bounded, it literally goes to 0 here, then what that means is that actually I can express this as a discrete Fourier transform. Now, discrete Fourier transform, of course, by its very nature, include, when you take the discrete Fourier transform of something like this, really there are these sort of ghost parts of the Fourier transform because you're assuming this is periodic and then this has to be periodic. So your Fourier transform has to be repeated over and over and over, spaced by 2kc. But that's fine as long as your Fourier transform actually goes to 0 before this point, because then your mirror here won't leak in to your actual estimate of the Fourier transform. However, if that's not the case, if your Fourier transform leaks out of this, then this mirror, on both sides in fact, will leak in. And what does this mean? This means that your high frequency modes in your image are going to look like lower frequency modes. So you're aliasing small scale power into large scale power. So the simplest example of this is as follows. If I imagine I have a sine wave, but I'm sampling it at something more like, a little bit bigger than its actual frequency, then I'll sample it here, and I'll sample it here, and I'll sample it here. I never make enough of these. Here, I'll sample it here. And if I try to interpolate these in any way, I'll get some function that looks like that. And so all this small scale power in this sine wave looks in this sampling like some very large scale wave. And that's just coming from the fact that this mirror of your Fourier transform is bleeding in to the scales you're interested in. This is a very important general concept. This affects not only image analysis, but also when you're looking at large-scale structure and stuff like this. This is one of the reasons that people want to have big spherical-ish type samples when they do large-scale structure. If you do some, line of sight thing, or what's the word? What's the word for this? If you just do a single deep survey that's very thin, then what can happen is if there's a wave that's coming in if there's a large-scale structure component that's coming in like this, it might be very small scale in reality with a wave vector like this, but in your sample, it'll look like very large-scale structure. So this aliasing issue is a very general issue when you're studying really anything like that. So what are the practical consequences of this? Well, the interesting thing is that telescopes are naturally band. So this statement that all the power is within minus kc to kc is a statement that it's a band-limited image. This is what we mean by band-limited. And all telescopes have a natural band limit, right? Because this white line is a Fourier transform of the pupil. And the pupil is a finite thing. So the Fourier transform of this has to have some limit at which it goes to 0. Because there's some angle outside of which no light actually gets into your telescope. Or not angle, but some size outside which no light gets into your telescope. So all telescopes actually have a band limit. And for a space telescope, that's actually a highly relevant thing, right? So for HST, there is a pixel scale at which you are Nyquist limit. You're below the Nyquist frequency, so you're all good. Now for a ground-based telescope, it's a little more complicated and less clean, because if you have a 10-meter telescope, you don't want to build your instrument with a pixel scale such that your well, unless you're doing AO, in which case you do. But if you're a 10-meter telescope without adaptive optics, then you don't want to build your pixel scale so small that you're band limited for the telescope. You want to be roughly band limited for this 20 centimeters or whatever the largest size is for your site. And that 20 centimeters is kind of fuzzy, right? Because there is some coherence outside of that. And so there's not such, for a ground-based telescope, there's not such a clean band limit that's practically useful. Because in practice, you're going to Nyquist sample something like the atmospheric blurring, and that's only going to be an approximate band limit. But it's pretty close. And it's usually clear when this stuff becomes practically useful.
Excuse me.
Yeah.
Is this KC roughly of order of 1 over the pixel size?
Yes. It is pi over the pixel size. So I also said that this was a noisy sample, and it's worth talking about the noise a little bit, because the noise properties also are good to understand. And here I'm really going to be talking about noise in a CCD, which is our, I'm an optical astronomer, so I'm biased. But this is a fairly relevant thing, and not irrelevant for a bunch of similar devices. Usually this is dominated by Poisson noise in the number of electrons. And the number of electrons is equal to the number of photons. So the main source of noise is typically just there are so many photons coming down, into my telescope per second. I have integrated for 1,500 seconds, so there's some expected number there, and that will cause some distribution of the actual number. Now, there's also electronics that are reading out the CCD, and those electronics have some noise associated with them, and this is called read noise. So typically, a noise model is the mean number of electrons expected in your exposure plus r squared. Now, this mean number in detail looks like the following. Well, if you're looking at if there's some object that's contributing light at a certain pixel, then there's mean number of electrons associated with that. There's also a sky background, which is usually fairly uniform. And there's noise associated with that. In many cases, this is actually far larger than the number of object counts. And then there's also usually a dark current, meaning even if you didn't open the shutter of the camera, you just read the thing out, you would have some number of electrons.
Is that just because it's like at some finite temperature? So
Basically, yeah, that's right. One of the reasons it's nice to keep them at stable temperatures, so this is consistent. Now, when you're looking at a FITS image, like something you've gotten off of a telescope, typically, there'll be some integers in it. You'll have a file, you'll have an image, there'll be some integers. Those integers are usually not the number of electrons. They're usually, usually people call them counts, but they've gone through various things. Let's just call it an ABC. But this number of electrons has been converted into some number, by the device, and these are related by something called the gain. And whether this is divided by the gain to get that, or that's divided by the gain to get this, the safest thing to do is just to make sure you understand how people have defined it. I think that there is a very standard definition, which I never remember. So you just want to make sure you've got it right. So when you're looking at a Fitts image, you can always actually figure out some rough estimate of the noise in each pixel just by counting up the number of electrons in each pixel, or the counts in that pixel, relating it back to the number of electrons by the gain. And if you know the read noise, then you can reconstruct the noise in that pixel. Of course, you have to make sure that the image you're looking at includes the dark, or that you at least include that self-consistently. Now, a few things to remember in practice. One is that this number here, or rather the number you measure here, of course, will give you a biased estimate of the actual noise, typically, because you're using your measurement to estimate your noise, which always causes problems, right? The noise is actually the mean number. And since this is a Poisson distribution, in detail, if you look on average what your noise estimate is, your noise estimate will be biased relative to the actual noise. But it's usually good enough. So this, you can determine, this is usually pretty low order. So like you can model it as a polynomial or something like this. This, you don't actually know until you measure it.
Wait, why is the noise in the sky below order in a case in which, you're...
Well, the sky itself is low order. Meaning, what I mean by low order is if I make a plot of, this image, it'll look like this, and maybe your sky is doing that. Where actually that's usually, this is a vast exaggeration of what an image will typically look like. Right. What I mean by low order is that I can model this background by some very low order function.
Oh, okay, yeah, sure.
Yeah.
Sorry. But the noise itself, that doesn't say, it can be a low order function, but it can have a lot of noise.
Oh, yes. I don't mean it's small. I just mean that you can model it. Once you've detected some objects and masked them, you can model the background and estimate your noise across the image and split it up between what?
Nothing, no. Wait. Everything's perfect.
Okay, good. We have some experts here, so the pressure's on. There is sort of a street fighting technique. If you don't want to think about this, or you have some image whose provenance you don't know, which happens all too often. But it's worth knowing, because sometimes you don't really care about the details. You just want to do something with the image. You want some approximate noise. Or maybe all you're interested in is how good is this image? What is the typical noise? And then you can estimate the noise with the following relatively neat trick, which I learned from one of your old advisors. Which is, I can look at the image. Well, for some reason I'm writing it down in a two-dimensional way now. That's obviously a minus. if I just look at a whole bunch of pairs, and by a whole bunch I mean a few hundred pairs of pixels, I'm sure you've done this. Just a whole bunch of pairs of pixels offset from each other by some fixed length. And then just look at the difference between them, sum the squares, divide by 2, that'll be roughly equal to the noise. You want these to be separated by enough, but not too much. And you'll just throw them down randomly into the image, and you'll do like 500 of them or something, and then you'll get a pretty good estimate of sigma. And sometimes one of these will land in an object, and it will skew this a little bit, so it's not quite right. But this is a very, very fast way of estimating. If you have an 8,000 by 8,000 image, you don't want to make the histogram, measure the histogram, that's like 60 million pixels, it can be slow. If you just want a very, very quick estimate of what the noise is, you just sample it a few hundred times like this, and that will get a rough estimate of the noise. So those are sort of the general properties of images. I don't think I need this anymore. I'm sure I will in moments, but. So once we know that, we can sort of write down the general image analysis strategy. And the first thing is, as you might have already guessed based on how I was describing this, is that it's virtually always iterative in some way. For a typical image, you very rarely know enough about what's in the image a priori to do anything but some iterative thing where you figure out what the image is, and then, or rather your code does, and then it proceeds from there in some iterative way. And why is that? Well, it's because usually if you're at a ground-based telescope, your sky background is varying. You don't know before you take the image what the sky background is. You don't know what the conditions are. You don't know what the point spread function actually is at that moment. And also you don't know what your sources are, usually. And so you have to figure out a lot of things about your view of the sky before you actually can analyze the image properly. So usually there's a couple of passes through the image where you're just figuring stuff out about the image, and then you go back and you say, okay, I'm going to use that information to do some measurements of things that are interesting. Assuming you don't think that the sky background is inherently interesting. And so there's always some loop that looks something like this, and I don't mean that you iterate hundreds of times, I mean you iterate like 4 times, or 3 or something, where you subtract sky, and bias and all this, you detect some objects, you measure them in some way, you determine or redetermine the PSF, and then when you know where the objects are that you detected in this pass, you've measured something about them, you know something about the PSF, you can go back here, and you can usually do a better job of subtracting the sky, detecting the objects, measuring them, and then redetermining them. And included in this is star galaxy separation, which I won't really talk about today, but that's going to be what helps you determine your PSF. So whenever you, and this is true of all image analysis codes, they always go through 1 or 2 or 3 times to figure out the image and then go back and measure it.
And so what do they subtract on the first?
Oh, you just subtract the median. I mean, you can do better than that, but that's usually good enough. Now, I'm not going to talk too much about how to determine the sky, but typically once you know where there are objects, you can mask them, fit a low order polynomial, it's a linear model, you can use all the things I talked about in February or something to actually fit that background and create some simple low order linear model for the sky. But what I want to talk about today is how to detect objects, because I think this is a particularly important one to understand if you're trying to if you're trying to do image analysis on your own, certainly, but even when you're trying to use some of the popular image analysis software that's out there, I think it's important to understand the fundamentals of detecting objects before you use those, because they have options which are entirely wrong, and they allow you to make terrible, terrible mistakes. So, first of all, you assume you've got a decently sky-subtracted image, and then, basically, you have some image that looks like this, and you want to figure out where the objects are. It's obvious where the objects are, right? They're there. But you want the computer to do this, and you want to do it in an effective way, so you find even the small things down to the limits of the noise. You want to know whether this is a real object or a fake object. And the most effective method to do this is using a matched filter. I don't know if somebody talked about matched filters over the past couple of months. Nobody talked about matched filters. It's a very common technique. And so I'll describe it here in this particular case, but in fact, it's a very, very general technique for finding things. And for PSFs, it's very, very straightforward. Let's say I just wanted to find things that were point sources in this image. And if I find the things that are point sources, I'm going to find a lot of the things that aren't point sources too. But I won't necessarily find all the detectable things that aren't point sources. Right? If I have something that's very much broader than a point source and low flux, it may be very detectable in this image, but the point source finding technique I'll describe right now won't necessarily work. And for the moment, let's assume Gaussian noise. In most cases, your sky background is high enough that your Poisson distribution is actually close to Gaussian. There are a number of instruments out there which don't do that, like the far UV channel of Galax. There's almost no background in the far UV, so it's usually 0, 0, 0, 1, 0, 0, 0, 0, 1. And so things get more complicated in that case. But in most cases, you have something where there's a lot of sky background, and so your noise is roughly Gaussian. In addition, it's sufficient to treat the noise as just due to the sky. And in fact, I'll talk about the noise in this context as being constant. It's easy enough to adjust what I'll write down here for non-constant noise, although it's not always a good idea. But for example, in reality, the noise will be larger in these areas. But for the purposes of detecting the objects, you don't really care. And it's sufficient to treat the noise as just due to the sky over the whole image. So, what the matched filter does is it says, at each pixel, what is the likelihood ratio between the best fit point source at this location and no source. So you take two hypotheses. One is that there's a point source with some flux. you fit for that flux, and that you compare that hypothesis to there's no source here at all. And you do this at each pixel. And if that likelihood ratio is high, then you say it's a detected pixel. And you do not do that by looping over each pixel and asking this operation. There's a much more efficient way of doing that. So I'm going to write here, so I'm going to, just for convenience, I'm going to write Fij is the PSF, assuming, well, I can do it this way. Fij is the PSF value at pixel I, given that there's a source at pixel centered at pixel j. And then I can write down, I can ask, okay, let me do this fit. Let me fit a point source at this location. I can write this fit using the techniques I talked about several months ago, which I'm sure you remember. This is chi-squared at pixel j minus so the chi-squared is just your PSF model times A, and A is just the flux of the best fit flux, minus the, let me call it the image at I can't call it that. Sorry, my notation sucks. Let me call this MI. Let me call it SI, the signal at I. So this is the chi-squared at pixel j, given that there's, given you've done this best fit. Now, of course, you do that best fit by asking, when does this equal 0? The math there is very simple. It tells you that A is Fi Si over sum over Fi squared, right? It's just a linear fit. So you get the normal linear regression formula. And then when you plug this back in, it's relatively straightforward to show that this is actually equal to Si squared over sigma squared, this is all summed over all I, minus A squared, sum over I, Fi squared over sigma squared. So if I expand this out, use this relationship, I can recover this function. Notice that this is constant, independent of A. And in fact, I can talk about, now I can write down the chi-squared assuming no source, chi squared not j, and of course that's just A equal this thing with A equals 0. And so that means that my likelihood ratio is the likelihood of a source existing versus a source not existing is equal to e to the minus chi squared j, this is at j, right? So my likelihood is just related to the chi squared in this fashion. And if I call this difference, I can write this as e to the delta chi squared over 2 at j. And then this delta chi squared at j is equal to this thing, and if I plug this into here, I can write this as the sum over fi si squared over sigma squared, sum over fi squared. So all I have to do is at each j, this is Fij, sorry. These are all Fij's. Sorry. At each j, at each pixel, I have to evaluate this. Right? Yeah.
So do we assume that each is that there is only one point source, or it doesn't matter?
Well, it doesn't matter if there's one. If there's only one at that location, it really doesn't matter. Sorry, if there's more than one at that pixel, it doesn't matter. But the hypothesis you're testing is that there is a point source or a sum of point sources at that location versus there's none at that location.
But what sources at other locations? Do we assume?
Oh, well, they'll bleed in. And so if I have two sources that are close to each other, you know, my chi-squared will be affected by that.
So in these A, so I should have another A.
No, you don't want to do that. You just want to assume, you just want to ask the question, what is the chances of having a point source here?
Because you're doing
And maybe you'll have a detected pixel because there are two small things that are overlapping. But that's okay.
I mean, in theory, if you knew Fij perfectly, you could distinguish two point sources of adjacent pixels.
No, because you're doing it pixel by pixel.
Right, but
So
if
you
you have a
only have to
pixel at
Right, but
J
you do
and
that
J-
later. You can do that, but you do that later.
Yeah.
Right? In this stage, you're just trying to find things which are plausibly have a point source in them.
So that,
And if there's more than one point source there in reality, you'll still get the pixel detected,
And if there's
which
more
is
than,
the goal here.
if there's more than one source in one pixel, that's completely equivalent to having a brighter source.
Right. Yeah. Exactly.
sorry, but who gives you this PSF that you start with?
Well, you do this, and then you measure the objects, and you find your smallest objects, and then you say those must be stars, and you estimate the PSF from that. And then you go back,
Yeah,
and you do this again.
I understand this, but what about the first iteration?
You assume it's basically Nyquist sample. What else are you going to do? It's tough when all you have are very faint things. So you run into problems there. If all you have in your field is very faint stars, just detectable stars, it's very difficult to do something with that image, and this whole process gets a lot harder. So you try to avoid that.
So don't you usually calibrate things, no, before mounting the telescope?
No. Oh well, I mean you do, but the only calibration that means anything in the end is the one you do after you measure all the objects, because the calibration will depend on the local conditions, right? It'll depend on like one of the biggest, the thing that varies the most is the atmospheric transparency. Your instrument also varies over time. But the atmospheric transparency can go up and down by 5% from night to night.
Sometimes the focus goes up and down by 5%.
Yes.
So this sounds like maybe a crazy idea, because I don't know anything about astronomy or telescopes. But would it ever be a good idea to mount like a giant light source that we know about on a satellite and shine it?
Yeah, that'd be a really good idea.
To actually model this?
Yeah. There are proposals to do that. Like you put a big hot piece of platinum up there with a thermometer in it.
To actually
And
get
then-
the sky
and then-
perfectly calibrated.
Well, that's to get the absolute calibration perfectly. But to to get the sky brightness, well, anyway, let's talk about calibration some other time. It's a whole different thing. But yeah, people have definitely talked about stuff like that. But particularly in the context of absolute calibration. So knowing, not just measuring the image and figuring out how to calibrate it relative to some standard, but to actually know what the actual flux is, which is really hard. But I want to finish this, because this, although it looks relatively complicated, is really quite simple. Because this thing here, Fij Si, which I can write as Yi, or Yj, sorry. Yj is equal to your image convolved with the PSF. And this, assuming your PSF is sufficiently compact, there are lots of efficient tools for doing this operation. So what this means is, if I define delta chi as just this thing, Fi, well, let me just call it now Yj over sigma, and then the square root of this thing. This is just your PSF convolved image. Remember, your image has already been convolved with the PSF when you observed it. Now you convolve with the PSF again, you get this image. There's a factor which, if the noise is constant, is actually just a constant factor which depends on your PSF, right? And the way to see that is if your PSF is very broad, then your PSF convolution will spread the light out very much, so the significance has to be scaled according to that. Sorry, I missed this is the 1 square root of that. But this then becomes a really trivial operation. You just convolve your image, and then you threshold it in some way that's related to your noise and your PSF. So, and this is what all detection algorithms do. And it's a very simple case of the general case of a matched filter. So this is a general statement about what a matched filter does. So when you look at people looking for dwarf galaxies in the stellar halo, or people looking for clusters of galaxies in in a redshift survey or in a photometric redshift survey, they'll very often use a matched filter technique. It's usually it typically comes down to something like this. And in the case of detecting objects in an image, it's just a really simple application of a matched filter. Now, there's a few important points about this. One is that if I do this, so I take this, I convolve it with the PSF, I get something like this. It looks like the same thing, except a little broader. If my threshold is here, and only one pixel satisfies it, say for these two objects, that's fine. We keep those objects, even if there's only one pixel. So you've got to beware of S-extractor in particular, because I think the defaults are that it has to have a few pixels in order that are contiguous in order to call it a detection. And that is, assuming you're using the right PSF, that's totally wrong and will screw up your fate source counts. You want to count things, even if there's only one pixel. Now, when you go back and measure this thing, then you've got to include all the stuff around it and say, I know there's an object there, because when I did my likelihood fit to this thing, I found that there was a significant detection. So I know, and there's a PSF that I know, so I know there's signal here because I saw the central pixel. So you have to include these pixels in whatever analysis you do. But you certainly don't throw that object away just because you only detected a single pixel. So that's a case where S-extractor, it has a set of defaults or a set of options, and I think it may even be the default, which will not do this. Will require a set of contiguous pixels, and that's wrong. Now the reason they do that is they're very often convolving with the wrong PSF. A PSF that's too small. And if you're doing that, then yes, you can very easily get false signals that are wrong when you're not convolving with the right PSF. And then you do, in order to get, not too many false positives, you actually need to require a bunch of pixels observed together.
Why is the PSF systematically underestimated?
Because the default just does a Nyquist sample thing, or even less, I think.
Yeah, that's interesting.
Right? So, now, the other thing to remember is that galaxies don't look like this. This is a horrible PSF. Galaxies look more like this. And this could, even if it were eminently detectable, if you do this operation, you might miss this galaxy. Because you're not using the right matched filter to get galaxies. So if you want to get faint galaxies, which are bigger than the PSF, usually you're saved by this at some level because your faint galaxies are actually small too. But if you want to get faint galaxies that are also large in angular extent, then you need to do something to actually detect those. So for example, in SDSS, there's a really dumb thing that's done, which works okay, which is to take this image, you just rebin it. Well, let me not even describe it that way. They just take the PSF and basically multiply its scale by 2, filter with that, after having subtracted out all the sources it had previously detected, and then redetects. And it does that 2 or 3 times with larger and larger effective PSFs. So it sort of looks with a larger matched filter to find groups of pixels which are all moving together, which if they were concentrated in a PSF, you might detect, but if they're not, you wouldn't notice it. So it uses a larger matched filter for the purposes of finding the lower surface brightness galaxies. And that procedure, although it's on its face ridiculous, actually works reasonably well.
And it's way faster than the alternative, right? Which is actually modeling the galaxy as something.
Yeah. Because the alternative, the PSF is usually, the PSF is typically a double Gaussian. Maybe it's got wings, but you usually ignore the wings. And so the Gaussians damp very quickly. Galaxies are, of course, exponential, which are much more annoying to, and don't even get me started on the blurs. So when do we usually end here? Is this an hour? Because this is a good place. This is a good place to end. Except I do want to say one more thing, which is about interpolation, because this is related to this issue of this being band limited data. If you have band limited data, if you want to, often one thing you want to do with an image is to resample it, because you have 2 images which are slightly offset and you want to add them together. And one thing to do is to resample the image and add them up. There's a number of reasons that can be very bad, so you want to think carefully whether that's the best way to do it. If you are going to do it, you do not want to interpolate linearly. You want to interpolate in some better informed way. And in the case of band limited data, there is, so whenever you do an interpolation, like linear interpolation is always, is basically modeling your data as some kernel like this. This turns out to be a very bad idea. But for band limited data, infinite or periodic band-limited data with no noise, the right way to interpolate would actually be with a sinc function. And you can prove this mathematically. So each kernel would look like a ringing sinc function that looked like this. Sine I x over delta minus n over pi in one dimension. So the sinc interpolation, where you're basically, you use each pixel to give you a coefficient to multiply this kernel by. This kernel goes to 0 at each of the other pixels. So you can just use this one pixel to determine this whole kernel, and then you do that in each of these, and then that gives you a way to interpolate between these. This would be the perfect way to interpolate if there were no noise and you had an infinite or periodic image. But given that there is noise, this is usually a bad idea, or a bad idea to do this alone. And usually you damp this with some Gaussian, some Gaussian thing with some sigma that's usually, I don't know, 5 or 10 pixels. That will damp any noise that's coming into this. But and if you use SWARP or one of these other things, it usually has an option which is similar to this, not exactly the same, that is usually not bad for a decently sampled image. But anyway, that's going to be too complicated for me to go much further, so we'll just leave it here. Thanks.